Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go with another awesome video. Today's video, what are we doing today? We are doing the covalent bonding worksheet number 4. It is not the last one, most certainly not. Before you watch this video, you need to have a periodic table with your valence electrons. Those go according to groups. That's in column 1, 2. That's for group 1. One valence electron. Group 2, two valence electrons. Group 3, 3. Group 4, four valence electrons. Group 5, five valence electrons. Group 6, six valence electrons. Group 7, seven valence electrons. Group 8, eight valence electrons. Those would be groups 1, 2, 13, 14, 15, 16, 17, and 18. If the number is greater than 10, you subtract 10 from it, and boom, there you go. The other thing you need most certainly here before you get started on this video is the following. You need this handout of mine, and that is the covalent bonding handout number 2, and it shows all this information on the axe. The axe is so important. And then you need the back side of it, and these are the steps in order to draw out Lewis dot structures. That's right. All right. Then the other thing you need to do before you actually start this video, since this is covalent bonding worksheet number 4, that's 4, count it 4, count it 4, count it 4, that's 4. In order for you to do and understand this, you need to do worksheet number 1. You need to do worksheet number 2. You need to do worksheet number 3. So you need to cover worksheet number 1, 2, and 3 before you get to 4. That would be highly advisable. Otherwise, you won't know what's going on. So, all right. So what we're going to do here, you know that today's video here is brought to you by, sponsored by none other than the Crazy Hat Chemist. That's me, the Crazy Hat Chemist. All right, so let's go moving on here and let's see if we can do this. So we're going to zoom on in here on this worksheet here. And so we get the best of all worlds here so that you can understand what is going on. All right, we're almost there. Getting pretty close. Getting pretty close. All right, fantastic. That's looking pretty good. Again, I am the Crazy Hat Chemist. This is where you need to get for all your Crazy Hat videos. All right, so this first one here is CH2O, and you can look up the name of this compound up online if you want to, but I'm going to tell it to you right now. Okay. When I was in a biology class way back in the day, they used this compound to preserve like all the creatures that you were cutting and slicing open. So formaldehyde. All right, you'll have to ask your instructor if that is necessary to know that information. Okay. All right. So the first thing that we're going to do is we're going to count up the number of valence electrons. How many carbons are there? There's one carbon. How many valence electrons in carbon? 4. Okay, so that's 4 valence electrons in carbon. How many hydrogens? That's 2 hydrogens. How many valence electrons in hydrogen? 1. Okay, perfecto. And that's 2. And then oxygens. How many oxygens? 1. How many valence electrons in oxygen? There's oxygen. That would be 6. 6. This is why you need that periodic table. We're going to sum all these up. That's a total of 12. And what does the Crazy Hat Chemist always do? Divide by 2, and that way we get 6 pairs of electrons. That's correct. All right. So now what we're going to do is we're going to follow the set of rules that I've outlined and guided you throughout this here. And that is right here. We are following these rules on the Lewis dot structures. And if you want a more detailed version of this, you're going to go to the Crazy Hat Chemist on YouTube. You're going to go to the Honors Chemistry 6 series of videos. That is the covalent, that is the bonding collection. That is the 6 video playlist in Honors Chemistry. And you're going to go to the video number 11, which is called Bonding 11 Lewis dot structure rules. And it gives you a stepwise answer of all those. So look that up, please. So we've counted up the number of electrons. We've got electron pairs, and then we're going to find the central atom. The central atom is the least electronegative, but never hydrogen. So it cannot be the hydrogen. So it's either going to be the carbon or the oxygen. So the most electronegative element is fluorine. So fluorine is the most electronegative element. And then we have, if we look, let me get a new periodic table, and hopefully that will help you out discern this. Okay, here's our new periodic table here, and we have a fluorine. So what are we going to do? We're going to compare everything to fluorine. That's right. Why fluorine? Because fluorine is the most electronegative element, and it will not go in the middle. So in this particular case, we have either carbon or oxygen. Those are our two options. And we're going to draw a line in between the fluorine and the oxygen, and then we're going to draw a line in between the carbon and the fluorine. Which line is longer? That is carbon. The carbon line is longer. Therefore, it is the furthest from fluorine. It is the least electronegative. The least electronegative goes in the middle. That's why carbon goes in the middle. The least electronegative goes in the middle, but never hydrogen. So that's why it's not hydrogen, and that's why it is the carbon, because the oxygen is more electronegative than the carbon. All right, now the other elements, like the previous videos, we're going to draw the sign of the cross, or X marks the spot, and the other elements go in these positions of 3 o'clock, 6 o'clock, 9 o'clock, or 12 o'clock. And we have two hydrogens, so that would be 1, 2 hydrogens in the 3 and 6 o'clock position, and then the oxygen in the 9 o'clock position. And to be perfectly honest, it actually does not matter where you place the hydrogens or the oxygens. I'm just trying to follow a particular pattern here for you so that you follow that every single time. Now what we're going to do is we're going to place electrons as is appropriate. So according to the rules, we're going to place bonding pairs of electrons between the central atom and the outside atom. Central atom, outside atom. Central atom, outside atom. Central atom, outside atom. The next rule is to place lone pairs of electrons on the outside atoms. And so you cannot place lone pairs on the hydrogens. Why not? Because hydrogen follows a duet rule. And on the previous videos, I've circled this hydrogen. And how many electrons are around this hydrogen? That one single line represents 2 electrons. So that's already a duet. So I cannot place lone pairs on that hydrogen. That would be violating the duet rule. So that's a no. So that's why I'm going to scratch that out. Right? So the next rule is to place, and this is the continuation of that same rule, lone pairs on the outside atoms. Well, I can place lone pairs on this oxygen. So I'm going to do 1 and 2. And then this next one I'm going to do in pencil, and that will be 3. And you'll understand why in just a moment. Okay. Perfect. I've used up my 6 pairs of electrons, and I'll verify that. That's 1, 2, 3, 4, 5, and 6 pairs of electrons. I'm going to validate the duet rule for hydrogen and hydrogen only. That's a duet. That's a duet. I'm going to verify the octet rule for all other elements. That's 2, 4, 6, and 8. And then the octet rule for all other elements. That's 2, 4, 6. Oh my. This is a problem. You should see that carbon is lacking an octet, and carbon must have an octet. Oxygen has an octet. So here is where we have the possibility of multiple bonds. And multiple bonds are when sharing is caring, truly. And so what we're going to do is you see that these circles that I have drawn here, I am going to make sure that both circles with the oxygen and the carbon have 8 electrons in each circle. So that's why I'm going to maintain the circles, but I've drawn this lone pair of electrons in pencil right here. What we're going to do is erase that lone pair of electrons that was in pencil on that oxygen, that last pair that I drew, and then I am going to put them within the carbon circle, and yet at the same time keep them in the oxygen circle. That will be a bonding pair of electrons. Now let's validate the octet rule for both the carbon and the oxygen. So the oxygen had an octet. Does it still have an octet? That's 2, 4, 6, 8. It still has an octet. Does Carbon had only 6 electrons and not an octet. Does it have an octet now? 2, 4, 6, 8. It does have an octet now. So that is correct. Now I'm going to erase my circles here. Now you should see my Lewis dot structure for formaldehyde. Perfect. Now what we're going to do is we're going to draw the axe. That's the AXE. And the central element is the A. So that carbon is the A. The outside elements, and it doesn't matter which ones they are or which ones what they are. And so those are X's. So there's a hydrogen, there's an oxygen. Those are all the same X, and that's 1, 2, and 3 things around it. Are there any lone pairs on the central atom that is the carbon? That answer is no. So there is no E. So now what we're going to do is we're going to look on the table that I have given you, or you should have. If you don't have it, you should look on my website, okay, or my other videos. And we are going to find what AX3 represents. So what does AX3 represent? That is the question. So we need this little table right here. And we're going to find AX3. I'm going to highlight that in a new color here. That will be orange. So AX3 is trigonal or trigonal planar. So I'm going to write that down. That's trigonal or trigonal planar. Perfect. What's the bond angle if it is AX3 and trigonal planar? What's the bond angle? That would be always 120 degrees. Excellent. 120 degrees. Now you noticed on my little table there's an asterisk, and that asterisk for the molecular polarity, it says if the molecule or ion is asymmetrical, then the molecule or ion is polar. If the molecule or ion is symmetrical, then the molecule or ion is nonpolar. So that's why there's that asterisk. So what we have to do is we actually have to build the model, and then from there, then we're going to work. So here is the model, and I'm trying to show this model in the same orientation of which you see that Lewis dot structure. That is, these are the 2 hydrogens. There's the oxygen. That's the carbon. You should see the double bond right here in between the carbon and the oxygen. And let's move this on up just a little bit here. Here's another model, and this one shows the same kind of structure here, right? All right, fantastic. So now what we need to do is ask ourselves the question, is this symmetrical or asymmetrical? So if I touch all the atoms on the outside with my fingers, are they the same atoms? Well, that's hydrogen, that's oxygen. The answer is no. So since that is a no, that means that is asymmetrical. Asymmetrical. Asymmetrical means it is polar. So it's asymmetrical and therefore polar. And so this molecule here of formaldehyde is asymmetrical and polar. Really, what this has is a molecular dipole moving in that direction there. This is the negative end of that dipole. This is the positive end of that dipole. That's a molecular dipole moving in that direction. Okay, that molecular dipole gives me a polar structure. Okay, that's formaldehyde. Let's do the next one. All right, the next one is hydrogen cyanide. It's a very toxic gas, by the way, bad stuff. Okay, so hydrogen, there's 1 hydrogen. How many valence electrons in hydrogen? Well, as always, there's 1. So that's 1 times 1, that's going to equal 1. Carbon, there's 1 carbon. Valence electrons in carbon, 4. That's 4 equals 4. Nitrogen, there's 1 nitrogen. How many valence electrons in nitrogen? That's 5. 5. Okay, we're going to add all these up. What do I get? The magic number of 10. And as always, the Crazy Hat Chemist tells you to divide by 2, and that will give you 5 pair. All right. Now, the least electronegative element goes in the middle, but never hydrogen. So I'm going to skip the hydrogen. And then what we're going to do is we're going to look on our periodic table, and we're going to compare the distance between fluorine and carbon. fluorine and nitrogen. So fluorine and carbon, or fluorine and nitrogen. Which is the longer distance, the blue line or the orange line? Well, the longer distance is the orange line, and that's the carbon. That means that carbon is the least electronegative element, and the carbon is king, and it goes in the middle, just like that. Perfect. All right, now what we're going to do is we're going to place these elements around it. And it really doesn't matter how you place them around it, but we're going to place them around it. And we're going to go that nitrogen in the 3 o'clock, and then in the 6 o'clock, this hydrogen. We could have placed the hydrogen in the 3 o'clock and the nitrogen in the 6 o'clock, or we could have placed them in a line, either horizontally or vertically, one or the other. It doesn't really matter. Again, you're going to be following these sets of rules here of the Lewis dot structure sequential steps. If you want to look at this in more detail, go to my Honors Chemistry 6, the bonding collection, video number 11, Lewis dot structure rules, where I spell them out for you quite nicely. Okay, but I'm just going to be applying it right now. So the first thing is bonding pairs of electrons between the central and the outside elements, bonding pairs of electrons between the central and the outside elements. So what I have done is I've used up 2 of my, that's 1, 2 of my 5 pair. I have 3 more pair yet to do. So the next rule is to put lone pairs of electrons on the outside elements. And again, hydrogen, if you've followed all the other videos and this one, hydrogen has a duet. It already has a duet, so don't add any more there. But nitrogen does not. So I'm going to place a pair of electrons around that nitrogen. That's 1 of the 3 remaining. So that's a total of 1, 2, 3. Then there's 4, then 5, then, 1, 2, 3, 4, 5. There we go. So 5 pairs. I'll do that again. 1, 2, 3, 4, and 5 pairs of electrons. Now this time again, I have used a pencil because I do know that I need to be moving things around. I'm going to circle around this hydrogen, and hydrogen follows what's called the duet rule, and that is a duet. Nitrogen follows what's called the octet rule, and that's 8. So 2, 4, 6, 8. That nitrogen has an octet. Then this carbon follows what's called the octet rule, and it has 2, 4. So it is lacking electrons. So that's a problem. Carbon must have an octet. It does not. I need to make it so that it does have an octet. So what we're going to do is what we did similar with formaldehyde. We moved a pair of electrons. We're going to do the same thing here. What we're going to do is we're going to move this pair of electrons. We're going to keep it in the circle of the nitrogen, but add it to the circle of the carbon. So we're going to move it into here like that. That will give me a line right there like that. I will have to erase this pair when I do that. Okay, now you should see that the nitrogen still has 8, which is 2, 4, 6, 8. But the carbon had 4 total electrons, and now it has 2, 4, and 6. That's still not enough. So I'm going to do this one more time. I'm going to take this pair and bring it in here to this. And now I will have the following. That's line right there. And what do I have to do is scratch that out. So what I'm going to do is I am going to now erase all the pencil marks that you see before you. And then what we're going to do is redo those pencil marks so that you can really see them clearly. Around this nitrogen, 2, 4, 6, 8 electrons. Around this carbon, 2, 4, 6, 8 electrons. Around this hydrogen, 2. That's duet rule. That's perfect. That is perfect for hydrogen cyanide. Okay. Now, I'm going to draw this another way, just in case if you are one of those special A students. And here is another optional drawing for you. I'm going to have that carbon, the nitrogen, the hydrogen. I'm going to have it in a line. And then I'm going to have that here, and then these 3 here, and then that right there like that. That is another way to draw it. Either way is perfectly fine. We're going to come up with the axe, A-X-E. So the A is the central element. That is the carbon in this particular case. That is an A. There's always an A. The X's are the two elements that are surrounding, that are physically attached to the central element. That's the nitrogen and the hydrogen. That's X2, because there's a nitrogen and a hydrogen. That's two of them. Are there any lone pairs on the central element? That's a no, so there are no E's. Then what we're going to do is we're going to look at this data table that you should have, and that's AX2. AX2 is the molecular geometry or shape of linear. So we're going to write down linear. And we're going to write down the bond angle that is linear, which is 180 degrees. 180 degrees. And then we need to figure out whether it's polar or non-polar because of that asterisk. So what we've got to first do is come up with the structure for this hydrogen cyanide. And I've done this here for you already. Here it is. I'm going to scroll this on up just a little bit so that we can see this. This is the lone pair of electrons on the nitrogen. This blue is the nitrogen. There are three of these here. That is the triple bond between the nitrogen and the carbon. And that black one is the carbon. This is the single bond between the carbon and the hydrogen. The white one is the hydrogen. So this is a linear type of molecule here. Hopefully you see that. Then what we're going to do is we're going to figure out if it's symmetrical or asymmetrical. So on the outside elements, I got my central element, the carbon. The outside elements, are they the same or are they different? They are different. So that means that this is asymmetrical. And that means that this is polar. Okay, fantastic. All right, we've done hydrogen cyanide. Very interesting one. I want you to see that that's a double bond there with the formaldehyde, and now you got that triple bond. Excellent. All right, let's pull these away. We've done double bonds and triple bonds before on a previous worksheet, so yeah. Okay, the next one is carbon monoxide, and I wrote out the name, but I didn't do the structure for you, and so let's see if we can do that. Okay, so carbon mono is for one, so it's carbon monoxide. There we go. You should be familiar with this. You should have a carbon monoxide detector inside your house, and make sure that the batteries are changed every 6 months so that if there is a problem with carbon monoxide in your house, you don't want to perish in your sleep because you just get tired and you fall asleep and you never wake up. So make sure that your carbon monoxide detector is actually working. How many carbons are in this formula? One. So there's one carbon. What are the valence electrons in carbon? How many valence electrons in carbon? There are 4 valence electrons in carbon. So times 4. 1 times 4 is 4. Then how many oxygens? There's 1 oxygen. How many valence electrons in oxygen? That is 6. So there are 6 valence electrons in oxygen. And so I'm going to add those up. That's a total of 10. And as always, we are going to divide by 2, and that will give us 5 pair. Hey, did you know that today's video is sponsored by and brought to you by the Crazy Hat Chemist? That's me. I am the Crazy Hat Chemist. So today's video is sponsored by the Crazy Hat Chemist. Please like, subscribe, and did you notice that the comment section is out of control? The number of likes are phenomenal. So I greatly appreciate that. I greatly appreciate all your comments, all your likes. Thank you so very much. Hey, did you know that I actually make some cooking videos as well? I make some great bread, some great things there. So check out the cooking videos, the best pasta sauce in the world, and of course, the best flour tortillas. All right, so here we go. We're going to keep on going here. The least electronegative goes in the middle. So what's the least electronegative between carbon and oxygen? We've actually already answered this with the formaldehyde example, but we'll try it again. The most electronegative is fluorine. We got a difference between carbon and oxygen. Which one is farthest away from the fluorine? That's the carbon. That goes in the middle. So the carbon goes in the middle. And the oxygen goes next to it. Again, we are following this path right here. The X marks the spot or the sign of the cross, and that oxygen is going to go there like that. Beautiful. I'm going to erase those dashed pencil marks here because we don't really need those anymore since we put them there. Perfect. Now what we're going to do is follow the rules of electron placement. And the first rule is place a bonding pair of electrons between the central and the outside element. Then we're going to place lone pairs of electrons on the outside elements. So that would be 1, then 2, 3. So 1, 2, 3, 4. I cannot put any more electrons around that oxygen because it already has an octet. And now I'm going to have to place them around the carbon consequently. All right. I've used up my 5 pair. That's 1, 2, 3, 4, and 5. All right. So I am going to circle this oxygen to verify the octet rule. That's 2, 4, 6, 8. That's an octet. I'm going to circle this carbon to verify the octet rule. That's 2, 4. Oops. That is not an octet. So sharing is caring. So I'm going to move this pair of electrons and move it in and keep it with the oxygen because I don't want to remove them, but bring them into the carbon. And so that will be that second bond. That's a double bond. So I'm going to have to erase these when I do that. Then that is still having 8 electrons around this oxygen. That's 2, 4, 6, 8. Do I have more electrons than the carbon that I did before? Absolutely, but I don't have that octet. I had 2, 4 electrons before. Now I have 2, 4, 6 electrons, not quite an octet. I'm going to have to do this one more time. I'm going to have to take this pair of electrons and bring them in, and that will give me now a triple bond between these two. And then that will cancel this out right there. So I'm going to erase all the pencil marks, and you should see and I'm going to rewrite them on there in a different way to verify the octet rule. So I'm going to place this here circle around the oxygen and all the electrons around it. So that's 2, 4, 6, 8. That's an octet around the carbon. That's 2, 4, 6, 8. They both have an octet. Erase all that. And this is my Lewis dot structure for carbon monoxide. Right. We're going to write the AXE, A-X-E. And like on a previous video, I had mentioned that you need actually 3 atoms in order to have a molecular shape. This only has 2. So is there an A? Yes, that's the carbon. And then there's one single X. Now, if you look at my table right over here, there's nothing that has A and an X. There's AX2 is the first one, and that actually has 3 different elements, at least at the minimum. So this is no shape. Okay, so then we don't write a bond angle for that because it has no shape, but we most certainly can draw the model or make the model for this. And here is the model for this one here of carbon monoxide. Let me flip this the correct way. So the black one is representing the carbon, the red one is representing the oxygen. There's a triple bond between the oxygen and the carbon, and these tan paddles are representing the lone pairs of electrons. Some might say that this is linear in shape, and they are not incorrect. So if they say that this is linear and 180 degrees, I would be okay with that. You're going to refer to your instructor about that one. I'll go with no shape and no bond angle, or linear and 180. I'll either accept either one. What I do want to say is the polarity. So if I touch these two things right here, are they the same or different? I'm not touching the lone pairs because they're always the same. Touching these two things, are they the same or different? They are different. That is asymmetrical. And asymmetrical leads to polar. Okay. The most dangerous thing about carbon monoxide is that it binds more tightly to the hemoglobin molecule than oxygen does. And so the oxygen that you breathe cannot bind to hemoglobin because carbon monoxide is a stronger bond than oxygen to hemoglobin. And that's why it's a cumulative toxic gas of carbon monoxide. So be very careful about this. Again, this is why you have a carbon monoxide detector in your home. Change those batteries every 6 months, please, for your own safety. All right, let's do the next one here. The next one is carbon dioxide. So we've got a carbon, we got an oxide, and di is the prefix for 2, like mono is the prefix for 1. So that's why this is a 1, that's why this is a 2. Hopefully that was pretty simple there. A little bit of covalent nomenclature of binary non-metals. All right, so carbon, there is one carbon. How many valence electrons in carbon? Let's check that out. There's carbon. There are 4 valence electrons in carbon. That's 1 times 4. That is 4. There are 2 oxygens. How many valence electrons in oxygen? That's 6. That is 2 times 6. That's 12. I'm going to sum those numbers up, and I am going to get the magic number 16. As always, I divide by 2, and that will give me 8 pair that I'm going to work with. The least electronegative element goes in the middle, but never hydrogen. There are no hydrogens to speak of, so I don't need to worry about that. I'm going to look at carbon and oxygen. We already did this with the carbon monoxide, but we'll try it again. Okay. Carbon and oxygen. Which one is farthest from fluorine? Because fluorine is the most electronegative element. Which one is farther from the fluorine? That would be the carbon. That's why the carbon is king. That's why carbon goes in the middle. Perfect. Now, again, like always, X marks the spot, sign of the cross, whatever you want to do there on that one here. And carbon is in the middle. Then I got 2 oxygens. There's the 3 o'clock position, and there is the 6 o'clock position. Some might favor this model, and that is this linear fashion here, and you are more than welcome to do it like that as well, or even vertically. It doesn't matter. It's entirely up to you. All right, perfect. So now what we're going to do is we're going to place our electron pairs as is necessary. So first, bonding pairs of electrons between the central and the outside element, then lone pairs on the outside elements. So here we go. So that's 1, 2, 3, 4, 5, 6, 7, and finally 8 pair. Excellent. I'm going to circle each element and the surrounding electrons. So this oxygen has 2, 4, 6, 8 electrons around it. This oxygen right here has 2, 4, 6, 8 electrons around it. And then this carbon has 2, 4 electrons around it. That is not good. Carbon must have an octet. So what we're going to do is we're going to move these 2 electrons here and bring them in and keep them with this oxygen, but bring them into the carbon. We're going to do the same thing here, and that is this oxygen on the right has 2, 4, 6, 8 electrons around it like it did before. This carbon has 2, 4, 6, so 2 more electrons than what it did before. So that means we're going to bring in these 2 electrons and bring them into this carbon here, and we're going to form another double bond. This lower oxygen at 6 o'clock position has 2, 4, 6, 8 electrons. And now this carbon in the center has 2, 4, 6, 8 electrons. I'm going to erase all this here. And now you can see this Lewis dot structure a little bit better. Okay, I'm going to draw that Lewis dot structure over here with this one off to the side. I know it's kind of small, but hopefully you're okay with that. So we got 2 different variations on this Lewis dot structure. Perfect. All right, and now what we need to do is we need to do our axe. Okay, so our central element is the carbon. That is the A of the axe. Then I got things that are physically attached to that central carbon. Those are X's. How many X's that are physically attached to the carbon? That's this oxygen and this oxygen. That's 2. Are there any lone pairs on the central carbon? No, there's no E's. There are lone pairs on the outside elements, but they don't count as E's. So I'm going to find AX2 on my handout. Of course, you want this handout, shoot me an email. I'll email it to you if you are not one of my students. So there it is, AX2, linear, 180 degrees. We got to look at the polarity. So this is linear for AX2. AX2 linear 180 degree bond angle. Oh yeah, that's perfect. Now let's build our model. So here is our model for carbon dioxide. Okay, so I'm going to scroll this on up here just a little bit here so we have a little bit more space, but this is for carbon dioxide. So you should see that this is the black one representing the carbon, the reds are representing the oxygens. It doesn't have the lone pairs of electrons on here. Okay. And then if I touch the outside elements, all the outside elements, are they the same or different? They are the same. So since they are the same, that is symmetrical. Symmetrical means non-polar. And as one of my chemistry instructors, she said, no party for you if you're non-polar. Okay. So there it is. That is carbon dioxide. All right. When you're breathing out some carbon dioxide. There's a little extra carbon dioxide just for you because I love you that much, folks. All right, let's do the last one here. Just a note, the Crazy Hat Chemist, that's me. Like, subscribe, give me a thumbs up. I'd greatly appreciate that. Boron trichloride. Boron is B, the most exciting element on the universe. In the entire universe, the most exciting element is boron. Hopefully you get that joke. Then we have tri. Tri is for three, like a tricycle, and chloride is Cl, so trichloride. All right. How many borons do you have? One. How many valence electrons in the most exciting element? There's boron, three. Three. All right. Then chlorines. You got three chlorines. How many valence electrons in chlorine? There's chlorine, seven valence electrons in chlorine. Oh, yeah. We are cooking now. So that is 1 times 3, that's 3, and 7 times 3, or 3 times 7, that's 7, 14, 21. I'm going to add those up, and I get 24. And as always, I can't count that high, so I'm going to divide by 2. That will give me 12 pair. The least electronegative element goes in the middle, but never hydrogen. There's no hydrogen, so I don't have to worry about that. I'm going to compare the distance between boron and fluorine and chlorine and fluorine, which is the farthest away, which gives me the longest distance. The longest distance is between the boron and the fluorine, so the boron is the central element, not the chlorine. So the boron is the central element. Then I'm going to place these other elements in the remember, the X marks the spot, the plus sign or sign of the cross. I'm going to place it in the 3 o'clock position, the 6 o'clock position, and the 9 o'clock position for those chlorines. I'm going to erase that sign of the cross, X marks the spot, plus sign. Got 12 pairs of electrons to place. So the rule is central element, outside element, central element, outside element, central element, outside element. That's 1, 2, 3 pairs of electrons so far. Then I'm going to place lone pairs on the outside element. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pair. I'm going to circle this chlorine. That has 2, 4, 6, 8. That's an octet. I'm going to circle this 6 o'clock chlorine. 2, 4, 6, 8. That's an octet. I'm going to circle this 9 o'clock chlorine. That's 2, 4, 6, 8. And now we're going to take just a little bit of a pause here. And I am going to circle this boron. This boron has 2, 4, 6. Is that an octet? No. So, couple of things here. Do we ever double bond a halogen? What are the halogens? Well, the halogens are the following elements here. The halogens are the fluorine, chlorine, bromine, and iodine. Do you ever double bond any one of these? The answer is absolutely not. So we cannot double bond any of those. And then we're going to go to my Lewis dot structure rules here, and I'm going to highlight something very important here. We're verifying the octet rule. Vast majority of elements follow that. I've said that they all do, but they don't all do. Okay. We are going to check for exceptions to the octet rule. Boron and beryllium can be electron deficient that is less than an octet, and that is acceptable. Boron can be less than an octet, and that is acceptable. That's okay. Perfect. So that is one of the rules of which we are following. So that's okay if that boron does not have an octet, and you will not double bond a chlorine ever. Okay, now we need to come up with the X for this. That's AXE. The A is the central boron, so there is an A. The X's, there are elements that are physically attached to that boron. There's one, two, three physical elements. Are there any lone pairs on the boron? That's no, so it's going to be AX. 3. I'm going to find AX3 on my handout. Again, if you need this handout, please watch my video here. It's in Honors Chemistry 6. That's the 6 playlist. It's called the Bonding Collection, and it's video number 28 is where this molecular geometry handout is. There's an expanded version of this. If you actually are not one of my students and you want this handout, then please shoot me an email, and I will email it to you as a PDF. Gratis, free, that is. So let's go back to the problem. That's AX3. So that's AX3. That's trigonal planar. Trigonal planar. And trigonal planar has what kind of bond angles? 120. 120 bond angles. And let's draw that, or let's make that structure, and here it is. And you should see that this is trigonal, that's trigonal, that's tri, 1, 2, 3, there's the tri part, and it's planar. That means all these atoms are in the same plane. You should see that they're all in the same plane. It's like, it's an airplane. Okay, so this is a bond angle of 120. This is a bond angle of 120, and this is a bond angle of 120. I'm going to touch all the outside elements. Are they the same or different? They're all the same. So that means that this is symmetrical. And that means it's non-polar. That's right, folks. Okay, quick little summary and recap of this entire worksheet here. I'm going to zoom on out so that you see the entire worksheet. This is the entire worksheet. We're going to start at the bottom with boron trichloride. Then we have carbon dioxide. Then we have carbon monoxide. Then we have hydrogen cyanide. And then we have formaldehyde. Those are the models. That's the worksheet. I'm hoping that that worked out really well for you. Please like, subscribe. I greatly appreciate that. Truly helps me out. That truly helps out if you like and subscribe and you let other people know that this is the place where you are learning your chemistry, then please let me know that. I greatly appreciate that. When you like and subscribe, it helps out to have other people find these videos. Thank you very much. Appreciate it. Hopefully you have a delightful day and a quick little spin here at the end. Let's see if we can spin the wheel of fortune. There we go. Isn't that beautiful? It's really not the wheel of fortune, but you get the idea. Great day. Bye for now.